In this session we study about the Pythagorean theorem. Look at on the screen that there are two pictures of great mathematician. One is Buddha and the other one is Pythagoras. So I want to tell you that what is the relation between Buddha and Pythagoras, the relation in their work on the same subject or the same title. Buddha's Salva Sutra in 1000 BC, before the birth of 500 years of the Pythagoras, was born, and Pythagoras has given the same theorem after the 500 years of Buddha's Salva Sutra. Now first I would like to explain you about the Pythagorean theorem. In a right angle triangle, the square of side opposite to right angle is equal to the sum of square of other two sides. So look at here, the PQR is a right angle triangle where Q is a right angle is equal to 90 degree, and the side opposite to right angle is PR. The measurement of this PR, the length of this PR is C. We are taking the square of this side, so we get here A3 is equal to C square, the square of this side is equal to the sum of square of the two sides. So we have the other two sides, PQ whose length is A and the QR whose length is B. The square of these two sides we take. The sum of square of these two sides is equal to the side opposite to right angle, C square. So this is the Pythagoras theorem. Now I would like to tell you about the Buddhayan Salva Sutra. Buddhayan Salva Sutra was written in 1000 BC by Buddha, an Indian mathematician. So it was written in Sanskrit in a slok form. So I would like to explain first this slok form. I would like to tell you what is it. So dirgha chaturasya chhana rajjupa sarvamani tranaha bhani cha yat parthagya bhute kuru taste dobhyam karoti. It means a rope stretched along the length of the diagonal produces an area which the vertical and horizontal sides make together. So this is just like a Pythagorean theorem. I would like to explain. This is our figure, a rectangle, and we stretch a rope along the diagonal, and the area made by this rope is equal to the area of the same this side B and area of this side A. The sum of area of these two sides is equal to the area of this side. So this is written here by the Buddha. A rope stretched along the length of the diagonal produces an area which the vertical and horizontal side make together. So this is written. In the other words, the same thing is given also in the slope. The chord which is stretched across a square produces an area double the size of the origin. So here also it is written about the square. If we take a square, just a moment. If we take a square ABCD and we stretch a diagonal here, and the area made by the square of this diagonal is double the area of original square. So here you see it is A, it is also A. So the area of this original square is A square. So if we take the area of this diagonal would be 2A square. You can easily judge it here. So now I would like to explain about the Pythagorean theorem. Now we will prove. We will see. So this is our Buddhayan slok, the Salva Sutra, which explains about this theorem, which was also written by Pythagoras. They both had done the work on same title and same subject. Now friends, we proved the Pythagorean theorem. You see here a triangle ABC, right angle triangle, right angle at B. So in a right angle triangle, the square of side opposite to right angle is equal to the sum of square of other two sides. So this we have to prove here. So first we see what is given to us. So given triangle ABC is given to us, and angle B is 90 degree, it is also given to us. These are given to us. Now to prove, we see what we have to prove now. We have to prove that the side opposite to right angle, the square of the side opposite to right angle, it means AC square, is equal to the sum of square of other two sides, AB square plus BC square. This we have to prove. Now there is some construction, so we have to construct something, construction. So we see, here we will draw a perpendicular from vertex B on AC. So I draw this perpendicular. These are perpendicular we have drawn. Just a moment. Let's change the color here. So this is the perpendicular, or give the name to this perpendicular is D. So look at here. So we have draw BD perpendicular on AC. Now we prove it. You see here. Now first we take a triangle ABC, the large triangle, and a small triangle on the left side, AB, AD, B. So we take the triangle in triangle ABC and triangle ADB. We prove the similarity between these two triangles. For proving it, we will apply here a similarity criterion, because the angle we have, we don't have the measurement of any side, so we will use the angle similarity criterion here. So in triangle ABC and ADB, you see the angle A is common here for ABC and for ADB. So we could write here that angle A is common, so we could write angle CAB in this triangle. CAB is equal to, in this triangle you see, BAD. It is BAD because common. Common angle is here. Now the second thing we see, angle B is right angle here also, and angle D is also right angle here. So we could write that angle ABC, is equal to angle ADB, 90 degree each. So we have got a criterion here, the angle criterion. We are proving that triangle ABC is similar to triangle ADB by a similarity. Now by the property of similarity, similarity triangle, we know that the ratio of their corresponding sides are equal. So we see the ratio of their corresponding sides. So here AB over AD AB over AD is equal to BC over DB. BC over DB is equal to AC over AB. So this ratio we have got here. This is our equation first we are writing here. So I explain you this thing here. AB over AD. AB is the angle opposite to right angle in this AB here in this triangle, large triangle ABC is the side on which the angle what we have taken and the right angle both lie. Now in a small triangle you see AD. AD is also the same thing, the right angle and there is a common angle is lie on this side. So similarly we see BC over DB. So BC in the right triangle is the side opposite to the common angle, and here BD is also the side opposite to the common angle. And the third one AC over AB. AC is the side opposite to right angle. Here also AB is the side opposite to right angle. The corresponding, the ratio of their corresponding sides are equal. They are proportional. So this we have got here. Now we similarly we see in triangle. Now in triangle ABC, again we are taking that large angle. Again we are choosing that large triangle and the small triangle of right hand side. This one we have to take. So we have taken ABC. Now BDC, ABC and BDC, and triangle BDC. So here we see in triangle ABC and BDC. In ABC, angle ABC is right angle, and BDC, angle BDC is also right angle, and angle C, here you see angle C is common in both. Angle C is common also in ABC and also in BDC. So we could write that here. Angle ABC is equal to angle BDC 90 degree each, and angle you see here angle C is common, so we could write that angle ACB, here we write that angle BCD. ACB and BCD both are equal. So angle ACB is equal to angle BCD common. Common angle for both ACB and BCD. Now by A criterion we have proved that triangle ABC is similar to triangle BDC. This we have proved by the property of similar triangles. Similar triangles, we know that the ratio of their corresponding sides would be equal. So we see AB over BD. We see AB over BD. So I write here AB over BD is equal to BC over DC. BC over DC is equal to AC over BC. So this is our second equation. Now what we have to do from this equation, first you see AB over AD and AC over AB, there is AB is common in both the equation, in both the ratios. So So in the first ratio you see AB in the numerator and the second ratio AB in the denominator. We choose these two ratios. This is not useful for us here. So we write here AB over AD is equal to AC over AB. Now we cross multiply AB to left side, so we get here AB square is equal to AC into AD. This is our third equation we have got. Now look at here also, AB over BD and BC over DC, and here also AC over BC. So here you see the BC over DC and AC over BC, their BC is common on both the ratio. So here BC in numerator, here BC in denominator. We choose these two. This is not useful for us, AB over BD. So we put here BC over DC is equal to AC over BC. So we take BC to left side. So we get here BC square is equal to AC into DC. Now this is our fourth equation. So now we add this third and fourth equation. So we get here, because we know that the third equation is I have written there AB square is equal to AC into AD. So first I change the color here. AB square is equal to AC into AD. This is our third equation. I just show you once more. AB square is equal to AC into AD square. The same thing I have written here. Now equation fourth I am going to write here. BC square is equal to AC into DC. This is our the fourth. Now adding these two equations. Adding these equations. So we add this, the left side we add here. So I adding it, AB square plus BC square is equal to AC into AD plus AC into DC. So you see AC we could take here common from both the terms. We get here AD plus DC. So it is AB square plus BC square. So now the AB square plus BC square is equal to AC we see AD plus DC what? It's max. So AD plus DC, it is AC. So we could write instead of AD plus DC, AC. So it is our AC. AC into AC, AC square so AB square plus BC square is equal to AC square. Now we have proved this theorem. This is our Pythagorean. Now we have proved this theorem. AB square plus BC square is equal to AC square. It was to be proved in this theorem. AC square is equal to AB square plus BC square. So in this way we could prove the Pythagorean theorem. It's very easy. Thank you.